In this movie, you will be introduced to write the first program in Systemverilog. Systemverilog is a hardware description language. A hardware description language, or HDL, is used to write the functional behavior of an IC in a high-level abstraction manner, and later this program is converted into the actual digital circuit by using complex tools in a process called synthesizing. If you are not familiar with the whole process of IC design and manufacturing, you may watch our YouTube video titled IC Design Process, a beginner's overview to VLSI technology, which is a 30-minute video explaining this whole process in a nutshell format. Systemverilog is an extension of Verilog hardware description language. Verilog was developed by a company called Gateway in 1980s, and later it was maintained by an NPA called Accelera. Accelera later extended Verilog to support more features for verification, and it is called Systemverilog HDL. The main focus of Systemverilog was initially to add a lot of verification features like object-oriented programming, but apart from that, Systemverilog added a lot of features to support design coding as well. Nowadays, Systemverilog is the most widely used HDL in the industry for both IC design and verification. Coming to the programming part, in Systemverilog, you will be writing everything in a programming block called module. A module is something similar to a function in C, where you will write all of your functional code in function when you write a C program. But remember that even though there is a main function in C, there is no such main module in Systemverilog. Whatever is the module that is coming after the top level module, that will be acting as your main module. So you can give whatever name you wanted to give your main module, and also you are free to write any number of modules in your program. In order to write a module, you will be using the keywords module and end module. Now let's see how to write a simple Systemverilog program to represent a simple digital hardware and how the hardware is mapped to the program that you are writing in Systemverilog. Now you will start to write the first Systemverilog program. As you know, Systemverilog is used to represent a hardware behavior, and therefore we will start by describing the behavior of the hardware and we will map it to a Systemverilog program. This is a hardware that you are going to model in Systemverilog. It is an 8-bit full adder. It has got 3 inputs called A, B and C in, and 2 outputs called sum and Cout, out of which the inputs A, B and the output sum are of width 8 and C in and Cout are of. Now let's see how to write Systemverilog program to write this hardware behavior. So here I am writing a module. The module name is adder, and these are the ports of this module. The ports of the module are, you can imagine it like the pins of the actual IC. So here the ports are A, B, C in, sum and Cout. So this is the actual program. We will describe each and every line in this program. Before writing actual functionality, you have to specify the direction of these ports in Systemverilog, because you are finally going to represent an actual hardware, and you have to specify whether these pins should be acting as input pin, output pin or an in-out pin. The direction is specified by using the keywords input or output, or if it is an in-out pin, you can even use in-out, and for every signal in this port list, you have to specify whether it is an input or output by giving these directions appropriately. So here the A, B and C are acting as input, and sum and Cout are acting as output. Next is the keyword logic. For every port, you have to specify whether it is a wire type or register type, and this is even true when it comes to a Verilog program. But in Systemverilog, there is an additional keyword called logic, and if you use the keyword logic, you don't need to worry about whether it is a wire type or register type. Now the question comes, what is wire type or register type? So this piece of code is finally represented as a hardware, and in a hardware, these ports can either be the physical wire that is going into another module or another part of IC, or even as the final output of the IC, or if this module is something that is coming in between a hardware, then this need to be connected to another part of your circuit, and there the actual A, B, C in and sum or Cout could be coming from different part of programs, which may be even registered. So you need to specify whether these should be acting as wire or register in the final behavior. But in Systemverilog, if you use the keyword logic, you don't need to worry about whether it is wire or register. the final synthesizing program will identify whether in this module instantiation, whether it need to be treated as a wire or register. In simple words, always use as input logic or output logic for listeners in Systemverilog. Now the last part in port declaration is the width of the signal. So here you have to make the width of the signals A, B and some as of width 8 because they need to be of 8-bit vectors in the actual hardware. So you have made all the signals as multi-vector by defining the signals as arrays, and just note the difference here how you define these arrays in Systemverilog, especially when you deal with hardware programming. So instead of just writing it as an array of signal by A of 8, something similar to a C program, you will be writing like 7 down to 0A. This is how you usually write multi-vector signals in Systemverilog, especially when you represent a hardware. After the port declaration, next part is the internal variable declarations. If at all some signals or some variables are needed in this program which are not coming as ports to this program, we need to define them before writing the functional part of your program. We will look into this result signal later, and now we will move to the functional description of the program. You can see that I am using the keyword assign before just writing a simple assignment statement, and again for simplicity there are two types of assignments in Systemverilog, either by using an assign statement or by using an always statement. As a short summary, you can always use an assign statement to represent a combinational logic, and you can use the always statement to represent either a combinational logic or a sequential logic. Now here our circuit is a simple combinational logic and we will be using the assign statement, but remember that all of your statement lines should be associated with either an assign statement or they should be within an always block in Systemverilog. That means if you're just writing like result is equal to A plus B plus C, then you'll get a compilation error in Systemverilog because they need to be always associated with either an assign or an always block. Now in the functional part, first you will be adding A, B and C in and assigning it to the internal signal named result, to the internal variable named result. And since result is a 9-bit vector, so 8 down to 0 means it's a 9-bit vector. So while you add A, B and C in, and if there is a carry overflow, that will be coming as the 9th bit of this result. And therefore your output sum will be equal to result of 7 down to 0 and your output Cout will be equal to result of 8. So finally at the end you will be using the keyword end module, and by using a colon you will be specifying the same name that you had given initially for this module. This is how you define a complete module in Systemverilog, and just to summarize here, first you will use the keyword module, next the name of the module which is given by you, next is a list of ports, so the port list separated by comma, and at the end there will be a semicolon. Next it comes as a port declaration where you will define the direction of each port and also optionally the width of each port, and usually you will define all of them as a logic type. After that you will be declaring all the internal signals used in this program, and finally you will be describing the functionality of the program. Always remember that they have to be associated either with an assign statement or you should write them in an always block. Now to give you a big picture, this is a representation of a 1-bit full adder with an input A, B and C in, and this will be the truth table of a 1-bit full adder. If you solve this truth table and implemented it as a digital circuit by using logic gates, it will look like this. And in order to implement an 8-bit full adder by using 8 different 1-bit full adder, you will connect them appropriately like something shown in this figure. The first carry out will be connected as the carry in of the second one, and the second carry out will be connected as carry in of the third one, and so on. And you know the diagram of a 1-bit full adder by using logic gates, and if you connect all these 1 bits appropriately as shown in that previous figure, you will implement a highly complex digital circuit. But by using a Systemverilog program that we had seen earlier, like this, you are actually implementing an 8-bit full adder. Here you haven't specified anything about the actual hardware, you haven't specified how the gates are connected, how many gates are used, you haven't given any such directions, but you have just used 3 simple lines of Systemverilog to represent this full adder. Now you might be wondering how this circuit is actually converted into an 8-bit full adder when the actual IC is produced. It is done by the synthesizing tool. When the synthesizing tool reads and decodes this line as some value is equal to addition of 3 other different signals, it will try to implement an adder circuit there. And by using the width of this left hand and right hand side variables, it will determine how big this adder should be. And finally, when the IC is produced, you will be getting the actual full adder circuit getting produced in the IC by using the correct combination of logic gates. That is, during the process of synthesis, the synthesizing tool will convert this line into an 8-bit full adder, and this is the beauty of using a hardware description language to represent the hardware behavior in a high-level manner. But in order to make it possible for the synthesizing tool to convert your program into the actual hardware, you have to follow certain restrictions in Systemverilog. You cannot use each and every feature that is available in Systemverilog to actually represent a hardware code. You have to write this code in such a way that it should be synthesizable. In this example, our circuit was a very simple one. It was just an 8-bit full adder. But in the actual world, you will be writing highly complex Systemverilog or HTL programs to represent highly complex digital circuit with lots and lots of modules and interconnecting these modules appropriately. Also, you will be using highly complex synthesizing tools to convert this program into the actual hardware circuit. This was an introduction to the programming in Systemverilog. This is presented by Systemverilog Academy, and if you like the video, please do subscribe our channel for more Systemverilog design, verification and UVM videos. Also, don't forget to take a look at the different playlists that we have created in our channel, which will teach a set of selected topics in Systemverilog. Thank you for watching.